Hello students, this is the 2024 Edexcel Computer Science GCSE paper. I'm going to go over it to help you with preparation for your GCSEs. Let's have a look at the first question. Computational thinking. Identify that means breaking a problem down, decomposition. Nice should be nice and simple. State two benefits of subprograms. So subprograms are both abstractions and decompositions because they hide the detail. So you don't need to know how something works if you're using a input statement or built-in subprogram into Python. You don't need to know how that works, other than you can use it anytime you like. And also you can use those subprograms to do a specific task, which could be like breaking a bigger problem down into smaller pieces. Two benefits of subprograms. They could be called many times, over and over again. Written once, which is huge. So user-defined functions, they can just need to be, or procedures. Return is when you have a function. Print is when you have a procedure. You can just make it once and then call upon it anytime you like. So they can be used by programmers who didn't have the knowledge to write those subprograms in the first place. They've been grouped into libraries. Reduces size, complexity of code. Loads of different reasons you can have here. Allows a team to work on a project. Lots of different answers you could have for 2 marks. Here is an algorithm that uses colors, right? So we've got array here because they're all the same data type. We've got a global variable and initialize an empty string. Main program, a for each loop. And then we have condition controlled loop. And then we've got conditional statements here. Let's have a look at the question. Give the first line number of a condition controlled loop. Well, I literally answered that just now. So you've got to know your terminology, okay, your tier 3 vocabulary. If you don't, then you're going to trip yourself up here. They're banking on you forgetting what the difference is between a for loop and a while loop. Give the first line number of an iteration. Anytime you hear iteration, it's going to be a for loop. So line 11 is that for loop. Give the line numbers, plural, of a selection. Do not be that student that only puts one number down. So selection, it starts on 16. So you could put 16 to 19. You could probably put 16, 18. That would give you the mark. Programs can have syntax errors and runtime errors. Define the term syntax error. So the best analogy to remember this, it breaks the rules, grammar, if you like, the grammar of the programming language. So obviously, if you're using JavaScript, you've got curly braces all the time. With Python, you've got colons and then indentations. So each language has its own sort of grammar rules, if you like. And if you're violating or breaking those, let's say you've got print and you don't put a closing bracket in there, immediately you haven't typed it correctly. What is a runtime error? Okay, so it tells you actually runtime errors happen when a program is executing. Explain a runtime error. So it's given you a bit of help here. Explain, you want to have usually with explain you have a because da da da. So 1 mark before and then the other mark after because. So you can say the program crashes or stops because an operation. So an operation the computer is asked to do is not possible. That's the best option there. Sometimes runtime errors happen because of logic errors, so the program runs technically, but it stops at some point because it can't complete. It could be a loop that never stops because a condition can never be met. Algorithms use relational and arithmetic operators. So the relational operators here state the two different results. Well, it's either going to be true or false, isn't it? There are no other options. Either count is greater than index or it's less than. So floor division is the same as truncating. When you take away the decimal point or something, so you get rid of decimal point. So 5 divided by 2 is 2.5. However, if we get rid of the decimal points, we end up with 2. So the answer is C. Programmers consider algorithm efficiency. Search. So there are only two, linear. So let me just write here, linear and binary. So which one is a divide and conquer algorithm? Binary is divide and conquer. So binary goes in here, binary search. Everything it has to be sorted in ascending order for binary search to work. Linear search works on unsorted lists. It's not as efficient. There are two sorting algorithms that we have, bubble sort and merge sort. Which one is not divide and conquer? Bubble sort. So the other one is merge, a merge sort, which needs also, you divide an array up and you divide it until you get single items and you build it back up again. Explain one effect the number of comparisons has on the execution time. These are pretty easy questions so far. The number of comparisons have on the execution time. Well, if you've got more comparisons, it's going to take longer, isn't it? So you can say a sorting algorithm takes longer if or executes, let's use better language, executes more slowly, because we always want to have that when you've got to explain, you want because a large amount of comparisons are made. Okay, pretty common sense, I would say. Data ASCII American Standard characters is used to represent letters and symbols. State the number of bits. 7, not 8. Extended ASCII is 8 bits. You're not going to get asked about that in GCSE. It's not going to be in there. So it's 7. ASCII code 64 represents A. What's 68? Well, 65, 66, 67, 68. If 65 is A, B, C, and D. Pardon me. You do not want to be getting questions like this wrong. You do not want to be getting questions like this wrong in your exam. Sound waves are converted to binary using sample intervals to define the sound. So if you've got amplitude over here and you've got time and you've got the sort of snapshots of your sample, whatever it is, how many snapshots you have, the interval is the gap in between. So it's like the gap in between samples. That's the interval. You could say the time, the measure as well. Give an expression to calculate the size of a bitmap image, not the size of the file. Okay, so really simple here. It's just width times height in pixels. That's all you need to do. So it would just be width times height. That is it. If you're actually doing the file size in bits, it would be width times height times bit depth. So far, this paper's been quite forgiving. Computers manipulate binary patterns, complete the table with the result of applying a shift to a binary pattern. So logical left shifts, arithmetic left shifts work the same way by 3. So let's just write it out. In fact, I'll write it out somewhere else, so we're not going to confuse ourselves. 0, 0, 1, 1. So if we move everything over by 1, we get 0, 1, 0, 1, 0, 0, 0, 1. Hang on. 0, 1, 0. If we move everything to the left by, we'll just do it 1 to begin with. So we've got, yeah, this one, sorry, my pen goes over here. So I'm just getting confused with my zeros and ones. Zero, zero, oh my gosh, 0, the stylus pen drives me crazy. 1, 1, and we fill the gaps with zeros. So if we go again, 1, 0, that zero's gone over here, that one's gone over here. 1, 0, 0, 0, 1, 1, 0, 0. So each time it's times in by 2. And then over here, 101. And then we'll end up with 0, 0, 0, 1, 1, 0, 0, 0. We've lost quite a lot of information on a logical shift by 3. Okay, arithmetic shift right by 2. What I would do in this situation is just literally work out what this is. So if we said that's the MSB, and that's minus 128, then that's going to be positive 64. That's positive 8, and that's positive 2. So then I could say, okay, well, minus 128 plus 64 is minus 64, plus 8 is minus 56, plus 2, minus 54. So this number is minus 54. And then what I'd expect is if I keep on moving it to the right, first of all, minus 27, and if I divide it again, I can't do it evenly, so I'm gonna lose some information. So we'll see what happens. Let me just show you how this works when you're using arithmetic right shift. You maintain the MSB, because that's always, for a minus number, it's always going to be 1, because that's got to be a minus 128. And then we've got a gap, and then this one goes over here. Then we've got 0, that's where the nibble is, 0, 1, yeah, 0, 0, 1, 0, 1. And now 0 over here has been chopped away, but we didn't really need it, so we've not lost any information, but we have to fill the gap with we have to fill that gap. I'll put using a different color there. We have to fill that gap with the value of the MSB. So what is this number? It's minus 128 plus 64, which is minus 64, plus 32, so minus 32, plus 4, so minus 28, plus 1, minus 27. So we've just proved to ourselves that by moving it over, arithmetic shift once is minus 27. Now if we move it over again, then we're going to have a gap, and then we've got 1, 1, 0, 0, 1, 0, and now this 1 has got nowhere for it to go, so it's going to be chopped away. So we've lost some information. So we've got to fill the gap with the MSB, with the value of the MSB. So we've got minus 128, plus 64 is minus 64, plus 32 is minus 32, plus 16 is minus 16, plus 2 is minus 14. So we can't have our minus 13.5 represented here properly. Obviously in real computing there are ways around this, but that's what we're looking for there in the answer. But prove it, work it out. Don't get a question like that wrong. It is 1 mark, but it's worth it. Identify the correct statement about overflow requiring more bits to store a result. There you go. That's the first one I was looking at. Easy. Now, technically speaking, you might cause a program to crash during an arithmetic operation. If you're trying to, there's a famous example of a rocket that tried to, I think it was meant to use 16-bit numbers, and one of the systems was 8-bit, and so it couldn't add the two numbers properly together or something like that, and as a result there was a crash in space. So if you're not able to, because you've got an overflow error or an underflow error or something like that, it can cause problems. So it's not great wording of this question, but that's the best answer, because you need more bits to store it in. So if you've got, 1, 1, 1, 1, 1, 1, 1, 1, and you're trying to add them all together, you're going to have a much bigger value that you can store in 8 bits. Convert the denary value plus 112. It's really simple. You just write out the base 2 values. And if you can't remember that, 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, 2 to the power of 5, 2 to the power of 6, 2 to the power of 7. The total amount of binary patterns would be 2 to the power of 8, because we can have 0 to the 127. If we're in this, anyway, that's beside the point. 2, 4, 5, 6, 7. Okay, so what do we need? We need 112. We don't need this because it's too big. We do need that. We do need that. So that's 96. We want 112. So 96 plus 16 is 102, 112. I think that's it, isn't it? So we need to have that. None of those. There you go. So what's the total amount you can have here? 255 is the biggest total positive integer, but we can have between 0 and 255, so 256 patterns, because you've got 0 as well, binary patterns. Right. Give the 8-bit binary 2 complement representation of minus 73. So the way to do it easily is to represent the positive 73. So you just have your, so this paper started off easy and it gets a little bit more complicated here. So what's 73? We don't want that, we do want that. So what do we have left? We just need a 6 and a 9. We need a 9. So we don't need those. So represent a positive value, then flip the bits. 1, 0, 1, 1, 0, 1, 1, 0, and add 1 to it. So 1, 1, 1, and that should be minus 73. Let's prove it. So that should be the value MSB is minus 128. All the others are positive. So we start off with minus 128. Then we add 32 to it. We add 16 to it. 48, 80, and then we've got 7 here. So we've got minus 80, and then we've got 4, 2 and 1 together is 7, and 80 plus 7 is a 73. So we can prove that we are looking at 70 minus 73 doing that way. I prefer that way. I think that's the best way to know how to use that system. Identify the number of bits. Okay, so we talked about patterns already today. Number of system symbols available in hexadecimal. No, hang on. Identify the number of symbols. Yeah, so we've got 0 to 15. So it's going to be hexadecimal, isn't it? It's a 16. Yeah, 0 to 15 because we've got 1 to 9. 0 to 9. A, B, C, D, E, and F, which is 15. The address bus of a computer is 8 bits wide. State the number of unique addresses that can be accessed. Okay, so it's very simple. We already looked at this. 2 to the power of 8, 256. So we had the answer when I was talking about this. Binary patterns of a 1 byte. Construct an expression to convert all those bytes to tebibytes. So you need to remember that a kebibyte equals 1024, 2 to the power of 10, right? Mebibyte equals 1024 squared. Just remember these, memorize them, the order of so 1024 cubed, and then 1024 to the power 4 is tebibyte. That's the key here. Okay, so if you can remember that, then all you need to do is divide this by 1024 to the power 4. You can also write this as 1024 times 1024 times 1024 times 1024. It's the same thing, okay? Neater to put to the power of the indices. Worth memorizing. Networks are described in different ways. Give the type of a network. Small geographical area is LAN, local area network. You might have a WAN, wide area network, and there'd be lots of LANs that are connected to it. Not to be confused with wireless, wide area network, okay? Name the characteristic of a wireless network measured in meters. Well, it's a bit of a weird question, but really it's just the range of it, of a wireless. Just think of your house, like you've got rooms that you won't get your signal in. Like sometimes the range can be a problem. Give 2 disadvantages of a bus network topology. Well, you've got 2 terminators, and then you've got all of these computers going off this one line. So it's best to just draw it out. It'll help you. So there are lots of errors. There are lots of problems with bus networks. If the whole network stops, if backbone fails, right? If this central line fails, then the whole thing doesn't work. That's the best option. Also, number of collisions. Goes up, increase, and just abbreviating here. If you've got more devices, and also only one device can transmit data at any time, and if these terminators are missing, the whole thing stops working. So there are all sorts of issues. The data sort of bounces up and down here, and it can cause collisions. Describe penetration testing. So white hat, black hat hackers. These are criminals. and these might be authorized to attack. So Apple might have authorized an attack on their system. Black box they're usually cyber criminals. Grey hats are sort of in between, but white hats are usually people that work in the company. Authorized attack. So to identify vulnerabilities. So it's carried out with the knowledge. With organization. Okay, white hat. Network protocols control rules of communication. Name a network protocol that transmissions from other electrical devices can interfere with. Well, we just talked about that, didn't we? I think the easiest answer is Wi-Fi or Bluetooth. I think that's the easiest answer there. Yeah, I can't see of anything else we could add there. Name the network. Okay, protocols is a bit more obscure, but the FTP, file transfer protocol, I think it's port 21. That's still used, even though it's pretty out of date. Other protocols are worth remembering are POP3, IMAP, where you have emails stored in a server, obviously FTP, and you've got things like HTTP, HTTPS, SMTP, sorry, SMTP for email, outgoing email. Worth remembering those protocols just in case they come up. Describe how the link layer of the TCP/IP. So the link layer is the last layer, and you've got the application. This is just for context. Transport, internet, and then the link layer. Okay, and then it all goes back to, again. So the link layer converts data to a suitable signal. So I light for fiber, so optic, or radio waves, or electrical, for copper wire. And it also receives data on the other end. It receives literally the zeros and ones. So the way I would remember the TCP/IP stack is that you're writing an email, and you start off with Outlook, right? You're writing your email, then you chop it up with your scissors into little packets, little jigsaw, and then you've got your routing, your IP, and you're sending it across the physical infrastructure of the internet, and then you've got to make sure that it's the zeros and ones themselves are going in the right way. So if you've got a fiber optic cable, there's got to be little pulses of light, packets of light. If it's a radio signal for Wi-Fi or something like that, it's got to be a radio signal. So then it goes all the way back again, link, internet, transport, and then back to Outlook, so someone receives the email on the other end. Construct an expression to calculate the transmission rate. So the way I remember this is speed equals distance divided by time. Easy formula from maths and physics, right? It's the best analogy, and distance is like the file size, and you might sometimes have to rearrange this equation. So construct an expression to calculate the transmission rate in megabits per second. Megabits, not bytes. Okay, when we're dealing with networks, it's megabits per second, required to transmit a 1.5 gigabyte. So we've got to be careful. We've got to remember, like we did earlier, what all of these are. 1024, 1024 to the power of 2, 1024 to the power of 3. You just got to remember that. 2 to the power of 10, 2 to the power of 20. You've got to remember all of this before your exam. So to get the sort of the distance, so size of the file, we need 1.4. It's because we're in bits per second, we want to times by 8 because there are 8 bits equals 1 byte, which we've seen already, and then times that by our 1024 to the power of 3. Okay, that's our numerator, and then divided by time, which will be 13 minutes. So that's 13 times 60 because it's per second, and it's mega, so we want to do 1000 squared. You could also do 1000 times 1000 or a million, right? So mega is a million. You've got to remember a mega is a million. Like if you've got 1 kilogram, right? That's an analogy to remember. Then it's 1000, isn't it? And then you've got a million, and you just keep on adding zeros, like 9 zeros. So if you had a 1 kilobyte, it's like a kilogram. 1000 megabyte. This is all base 10. 1 million, and then gigabyte is 9 zeros. But this is in base 2. It's not base 10. So you just got to remember the differences between those. It's one of those things it's worth doing before the exam. Okay, let's have a look. A compiler translates source code to machine code, which are just binary zeros and ones in a specific manufacturing orientation, HP or Apple. If the source code is edited, it must be recompiled. 2 other characteristics of a compiler. So you create the program. This could be in something like C++, which is a compiled language. Yes, the source code has to be recompiled if there are errors, because so at the very end, so we can say translates whole program in one go, and then we can say errors only reported at the end. Okay, we can only know that when it's done. And also, one cool thing is that we get an executable file at the end. So once you've compiled it, you can't really easily see the original code. It's just the machine code. So that's a super powerful thing, because you can companies can protect their innovations. That's why often they're using compiled languages. So that's another one you could have, another mark. Describe how an operating system organizes files and folders. Well, the way to remember this is like you've got a root of a tree, and then you've got the branches, and then you've got all these off. And remember this upside down. So if you thought, okay, what does it look like upside down? You have a root directory, sometimes known as a folder, and then you have these branches. That's the best way to remember it. So it's a hierarchical tree structure with a root node directory. Okay, that's the best way to remember. And each of these is a unique path that you can go down. So if you've got, say, I don't know, OneDrive, it's very likely at your school you might have a sort of root directory for OneDrive, and then all the folders sort of branching off it. Explain one way an audit trail helps programmers create robust software. So an audit trail, I mean, think of the word audit. So an audit trail keeps so let's say improves accountability. So that would be an odd, because we've got an explain command word, because it keeps track of changes. Now, you might have heard of something called Git. It's not GitHub, but you can, like in GitHub, you can see all the different iterations of what people have done at any particular time. It's a bit like that. So anytime you've amended or pushed and pulled something, there's a record of it and who did it and what was done. So it's you can go back to an earlier version, and that's a key part of open source software loaded on GitHub, that you can see the trail of who's done what at what point, and you can always refer back to an earlier version. Parking at an airport is controlled by computers. No paper tickets are issued. Here is an image of a control system at the exit, which would be an embedded system. The control system uses sensors, camera, and a database. Yes. The barrier lifts if the parking fee is paid or has been paid. Yeah. Describe what the system does when the exit sensor is activated. So it's just common sense. Just, think of what happens when you've got your car and you're driving up to this thing. What's going to happen if you're in the car and you drive up to that thing? A camera, you can say the camera, because it's told us there's a camera, reads. It's very simple, right? There should be a nice easy mark. Camera reads the reg, your license plate. Checks database. To see if fare has been paid. That's simple, and that's all there is to it. Nothing complicated in that question at all. Just 2 marks. Okay, your buses, you need to remember your buses for your fetch, decode, execute, and the general purpose computing von Neumann architecture. The clock will have a directional connection, so if you don't put an arrowhead in there, you're not getting the mark, okay? Into the CPU. Control bus is given for us. Confusingly, it's got 2 of these. So in almost all the literature, they say that the data bus is the bidirectional one. So that's a bit confusing of them. But address bus. So yeah, if they ask you a slightly different variation on this goes both ways. Bidirectional. This is at GCSE level, it's a very simplified version of what's going on, but yeah, that could potentially throw you off, which is naughty of them, to be honest with you. A company is developing a new smartphone. This is a 6 marker. A smartphone has built-in devices, including a camera and a sound recorder. The smartphone has applications, okay, including one to edit pictures and translate speech to a text file. And so discuss the characteristics of high and low level programming languages that make them suitable developing. Okay, so built-in devices and the application. So it's quite, what you really want to be doing here is to tell the examiner that you understand what the advantages of a low-level application. So it's also talking about embedded systems. So rather than being a general purpose computer, a smartphone does certain specific things. So we can talk about built in. You've got 2 bullet points. See if you can give 3 marks for each of those bullet points. I'm going to abbreviate a little bit here. So you could say low level language assembly, for example. Assembly language are microprocessor dependent, so machine code, machine code. So hardware, I'll put hardware specific. So if you've got an iPhone, the camera might be made by Sony, for example, not Apple at all, or it could be a Zeiss lens or something like that. So low-level languages are hardware specific, so you can more efficiently on a single chip. You can manipulate the hardware directly, and you could optimize it to reduce time. So hardware direct. I'm just abbreviating here. Reduce time as well. Smaller files, faster. High level languages would be good for like teams to work on them. So you could have like a design team working on aspects of it. You could have a compiler. So high level. You could talk about compiler to create executable code. High level have subprograms, libraries. So Python is perfect for this because there's so many things built in, like the math module and C math and all sorts of different things. NumPy, lots of different stuff. So Python's got lots of built-in libraries to allow direct access to certain devices as well, like microbits or some things like that. What else could you say? For applications, let's talk about applications. You could say the email app written in high-level language, like Python, because it makes the development much quicker. Much quicker. You could say and plus tools are already there. You could say portable to different phones. Specialized libraries for specific hardware. So I think the crux of that is low-level languages might be good to speak to specific components. They're faster, smaller file sizes. They're typically used in embedded systems for that reason. So there should be enough there to get your 6 marks. A replacement cycle is the time between the purchase of a device and the purchase of its replacement. Describe one impact, the length of the... Okay, so think of your new Apple iPhone 17s or 18s or whatever it is by now. If they're keeping the shareholders happy, they release one every year. Okay, do you really need one every year? No, you don't. What's the impact? Well, every time you create that new phone, it has to have lithium, cobalt, gold, um, loads of precious minerals, and lots of other things which would be difficult to manufacture and mine from the environment. Data centers, I mean, also more e-waste, electronic waste, more e-waste, more manufacturing. I mean, you'll have to put this into an actual sentence. Manufacturing. So you could say shorter replacement cycles lead to more manufacturing, which leads to increased mining and fossil fuel use, something like that. You want to link these together. IP, intellectual property, is protected by different methods. So a hardware invention, you get 20 years usually as a patent, and an advertising slogan is a trademark. So you might see TM, trademark. You could probably put copyright here and you get a mark, but trademark's the best answer there. Robots use sensors to collect data about their surroundings in order to carry out actions independently. Tesla is a classic example of essentially a robot that collects a lot of data around its surroundings, because they have microphones and cameras everywhere. Explain one way a modern car as a robot. So just think of your Tesla. But you can say wipers come on automatically. Lights come on automatically as well. They do in my car. Speed adjusted due to conditions. There might be to do with rain or obstacles, those kind of things. You could say temperature adjusted. Lots of things in there for 2 marks. Anti-malware protects systems from viruses. Here are flowcharts. Right, draw a flowchart in the box to show how an anti-malware detects a virus. Out of interest, sub-programs are denoted like this. If it ever comes up, probably won't. Okay, anti-malware. So we want to make sure we've got a deep database of signatures. That's the key here. So how will this work? We've got nothing, so we want to have a start and an end. Always start and an end. If they've not given those to you, just put them in, and always have the arrows with the direction, please. Always, without fail. So what do we do first? We have a process. We open suspect file. That's a process. So it's in our quadrilateral. Open our suspect file. Then we open signature file. So this is from a database of virus signatures. So it can tell, oh, it's very likely that this is a variant of a well-known virus, or it is the exact one on our database. So it could be literally the look of it, it could be they use certain tells in their Bitcoin address, or it could be the way they've written it, or they found one already and they added it to the database and they matched it against it. So here we have another process, compare suspect file with signature. Right, pretty simple so far. Let's go over here, and then all we need to do is to make a decision now. So found matches, either yes or no. Right, yes, or it's no. And if it's a no, put this down here, you can say file is clean and end it. Now this is a parallelogram because we've got output to the system. So I'm just going to put this around here. Process, put file into quarantine, which is like a safe place on the computer, and then tell the user what's going on. So you can say parallelogram output to the system, file is infected, and then end. Or let's say stop. It'd be best to say stop. Okay. Good. Let's carry on. Oh, that's it. I think we're done. So hopefully, I mean, the beginning of the paper wasn't too bad. It got a little bit difficult with the data. So, swings and roundabouts with these. Anyway, hopefully you did all right, and hopefully this helped.